Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase synchronous motors. By solving these problems, we shall learn how to determine induced EMF and input power of a three-phase synchronous motor. In a three-phase synchronous motor, field winding is excited with DC source and armature winding is connected to three-phase AC supply. Input power to the armature winding Pin equals to 3 times ETIA cos phi, where ET is the terminal voltage per phase, IA is the armature current per phase, and cos phi is the operating power factor. For star-connected armature winding, Pin equals to root 3 times VL into IA cos phi. Here VL is the line-to-line terminal voltage. Let us draw the per-phase equivalent circuit of a three-phase synchronous motor. From this circuit we can write induced EMF per phase E0 equals to ET minus IA into ZS, where synchronous impedance per phase ZS equals to RA plus JXS. Here RA is the armature resistance per phase and XS is the synchronous reactance per phase. ZS may be written in polar form as ZS at an angle theta Z, where magnitude of ZS equals to root over RA square plus XS square and impedance angle theta Z equals to tan inverse XS by RA. For star-connected armature winding, line-to-line induced EMF E0 line equals to root 3 times E0. From the expression of induced EMF per phase, we get armature current per phase IA equals to ET minus E0 divided by ZS. A 300 kilovolt ampere 6.6 kilovolt 50 Hz three-phase star-connected non-salient pole synchronous motor operates at full load with 0.866 leading power factor. It has synchronous reactance per phase of 20 ohm and armature resistance per phase of 1 ohm. We have to calculate the induced EMF and input power. Let us first write down the given data. Rating of the motor S equals to 300 kilovolt ampere, that is equal to 300 into 10 to the power 3 volt ampere. Line to line terminal voltage VL equals to 6.6 kilovolt, that is equal to 6600 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3, that is equal to 6600 divided by root 3, that gives us 3810.5 volt. Given armature resistance per phase RA equals to 1 ohm and synchronous reactance per phase XS equals to 20 ohm. Operating power factor cos phi equals to 0.866 leading. We know that VA rating of a three-phase synchronous motor S equals to root 3 times VL into IA. Therefore, armature current per phase IA equals to S divided by root 3 times VL. Using values we get 300 into 10 to the power 3 divided by root 3 into 6600. That gives us 26.2432 ampere. Let us now calculate input power. Pin equals to S times cos phi. Using values we get 300 into 0.866 equals to 259.8 kilowatt. Power factor angle phi equals to cos inverse 0.866 equals to 30 degree. Armature current per phase may be written in polar form as Ia equals to Ia at an angle phi, that is equal to 26.2432 ampere at an angle 30 degree. Now we shall write down synchronous impedance per phase in complex form. Zs equals to Ra plus Jxs, that is equal to 1 plus J20 ohm. This may be written in polar form as 20.025 ohm at an angle 87.1376 degree. Expression for induced EMF per phase E0 equals to Et minus Ia into Zs. Taking terminal voltage per phase Et as reference, we get E0 equals to 3810.5 at an angle 0 degree minus 26.2432 at an angle 30 degree into 20.025 at an angle 87.1376 degree. That gives us 4050.2 minus J 467.6675 volt. This may be written in polar form as 4077.11 volt at an angle minus 6.587 degree. Since the armature winding is star connected, line to line induced EMF E0 line equals to root 3 times E0, that is equal to root 3 into 4077.11, that gives us 7.062 into 10 to the power 3 volt or 7.062 kilovolt. Since the power factor is leading in nature, here we observe that E0 line is greater than VL. This condition is termed as overexcited condition. A 400 volt 50 Hz 3-phase star connected synchronous motor takes 52.5 ampere at 0.8 power factor leading. The motor has impedance of 0.25 plus J 3.2 ohm per phase. We have to calculate the induced EMF and input power. Let us first write down the given data. Line to line terminal voltage VL equals to 400 volts. Since the armature winding is star connected, terminal voltage per phase Et equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.9401 volt. Armature current Ia equals to 52.5 ampere and operating power factor cos phi equals to 0.8 leading. Given synchronous impedance per phase Zs equals to Ra plus Jxs equals to 0.25 plus J 3.2 ohm. This may be written in polar form as 3.2098 ohm at an angle 85.5328 degree. Let us now determine power factor angle. Phi equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in polar form as Ia equals to Ia at an angle phi, that is equal to 52.5 ampere at an angle 36.8699 degree. Expression for induced EMF per phase E0 equals to Et minus Ia into Zs. Taking terminal voltage per phase Et as reference, we get E0 equals to 230.9401 at an angle 0 degree minus 52.5 at an angle 36.8699 degree into 3.2098 at an angle 85.5328 degree. That gives us 321.24 minus J 142.28 volt. This may be written in polar form as 351.3366 volt at an angle minus 23.8882 degree. Since the armature winding is star connected, line to line induced EMF E0 line equals to root 3 times E0, that is equal to root 3 into 351.3366, that gives us 608.5328 volt. For a three-phase synchronous motor, expression for input power Pin equals to root 3 times VL into Ia cos phi. Using values we get root 3 into 400 into 52.5 into 0.8, that is equal to 29.098 into 10 to the power 3 watt or 29.098 kilowatt. On no load, the EMF of a 3.3 kilovolt, 50 Hz, three-phase star-connected 4-pole synchronous motor may be considered equal to and in phase with terminal voltage. If on the application of load, the EMF induced is retarded by 5-degree mechanical, we have to calculate armature current, power factor, and power supplied to the motor, taking synchronous reactance per phase be 25 ohm and the stator resistance be negligible. Let us first write down the given data. Line to line terminal voltage VL equals to 3.3 kilovolt, that is equal to 3300 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3, that is equal to 3300 divided by root 3, that gives us 1905.2559 volt. According to the problem statement, induced EMF per phase E0 equals to ET equals to 1905.2559 volt. Synchronous reactance per phase XS equals to 25 ohm. Torque angle delta equals to 5-degree mechanical. We know that theta electrical equals to P by 2 into theta mechanical. Given number of poles of the machine, P equals to 4. Therefore, delta equals to 4 upon 2 into 5 degree. That gives us 10 degree electrical. Induced EMF per phase may be written in polar form as E0 equals to E0 at an angle minus delta, that is equal to 1905.2559 volt at an angle minus 10 degree. Now we shall write down synchronous impedance per phase in complex form. Zs equals to Ra plus Jxs. Since the stator resistance is negligible, Zs equals to 0 plus J25 ohm. This may be written in polar form as 25 ohm at an angle 90 degree. Expression for induced EMF per phase E0 equals to Et minus Ia into Zs. Therefore, armature current per phase Ia equals to Et minus E0 divided by Zs. Taking terminal voltage per phase Et as reference, we get Ia equals to 1905.2559 at an angle 0 degree minus 1905.2559 at an angle minus 10 degree divided by 25 at an angle 90 degree. That gives us 13.2843 ampere at an angle minus 5 degree. Operating power factor of this motor cos phi equals to cos of 5 degree, that is equal to 0.9962 lagging. Now we shall calculate power supplied to the motor. P in equals to root 3 times VL into Ia cos phi. Using values we get root 3 into 3300 into 13.2843 into 0.9962, that is equal to 75.641 into 10 to the power 3 watt or 75.641 kilowatt. A three-phase star-connected non-salient pole synchronous motor connected to 2000-volt mains has an armature impedance of 0.2 plus J 2.2 ohm per phase. The excitation of the machine gives a generated EMF of 2500 volts. We have to calculate the line current, power factor, and power supplied to the motor when operating at a load angle of 20 degree electrical. Let us first write down the given data. Line-to-line terminal voltage VL equals to 2000 volts. Line-to-line generated EMF EL equals to 2500 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3, that is equal to 2000 divided by root 3, that gives us 1154.7 volt. Generated EMF per phase E0 equals to EL by root 3, that is equal to 2500 divided by root 3, that gives us 1443.4 volt. Given load angle delta equals to 20 degree electrical. Now we shall write down generated EMF per phase in polar form. E0 equals to E0 at an angle minus delta, that is equal to 1443.4 volt at an angle minus 20 degree. Given armature impedance per phase ZS equals to RA plus JXS, that is equal to 0.2 plus J 2.2 ohm. This may be written in polar form as 2.2091 ohm at an angle 84.8 degree. Expression for generated EMF per phase E0 equals to ET minus IA into ZS. Therefore, armature current per phase IA equals to ET minus E0 divided by ZS. Taking terminal voltage per phase ET as reference, we get IA equals to 1154.7 at an angle 0 degree minus 1443.4 at an angle minus 20 degree divided by 2.2091 at an angle 84.8 degree. That gives us 241.4 ampere at an angle 27.42 degree. Since the armature winding is star connected, armature current per phase IA equals to line current. Now we shall calculate operating power factor. Cos phi equals to cos of 27.42 42 degree, that is equal to 0.8877 leading. Power supplied to the motor P in equals to √3 times VL into Ia cos phi. Using values we get √3 into 2000 into 241.4 into 0.8877, that is equal to 742.325 into 10 to the power 3 watt, or 742.325 kilowatt. The input to an 11 kilovolt 50 Hz 3-phase star-connected synchronous motor is 60 ampere. The effective resistance and synchronous reactance per phase are 1 ohm and 30 ohm respectively. We have to determine the power supplied and the induced EMF for a power factor of 0.8 leading and 0.8 lagging. Let us first write down the given data. Line-to-line terminal voltage VL equals to 11 kilovolts, that is equal to 11,000 volts. Since the armature winding is star-connected, terminal voltage per phase ET equals to VL by √3, that is equal to 11,000 divided by √3, that gives us 6350.853 volt. Given armature current Ia equals to 60 ampere, effective armature resistance per phase Ra equals to 1 ohm, and synchronous reactance per phase Xs equals to 30 ohm. Let us now write down synchronous impedance per phase in complex form. Zs equals to Ra plus Jxs, that is equal to 1 plus J30 ohm. This may be written in polar form as 30.0167 ohm at an angle 88.09 degree. First case, when operating power factor cos phi 1 equals to 0.8 leading, power factor angle phi 1 equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in polar form as Ia1 equals to Ia at an angle phi 1, that is equal to 60 ampere at an angle 36.8699 degree. Expression for induced EMF per phase E01 equals to ET minus Ia1 into Zs. Taking terminal voltage per phase ET as reference, we get E01 equals to 6350.853 at an angle 0 degree minus 60 at an angle 36.8699 degree into 30.0167 at an angle 88.09 degree. That gives us 7383.8642 minus J 1475.2928 volt. This may be written in polar form as 7529.8 volt at an angle minus 11.3 degree. Since armature winding is star connected, line to line induced EMF E01 line equals to √3 times E01, that is equal to √3 into 7529.8, that gives us 13,042 volts or 13.042 kilovolt. Now we shall calculate power supplied to the motor P in 1 equals to √3 times VL into Ia cos phi 1. Using values we get √3 into 11,000 into 60 into 0.8, that gives us 914.5228 into 10 to the power 3 watt, or 914.5228 kilowatt. Second case, when operating power factor cos phi 2 equals to 0.8 lagging, power factor angle phi 2 equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in polar form as Ia2 equals to Ia at an angle minus phi 2, that is equal to 60 ampere at an angle minus 36.8699 degree. Expression for induced EMF per phase E02 equals to ET minus Ia2 into Zs. Using values we get 6350.853 at an angle 0 degree minus 60 at an angle minus 36.8699 degree into 30.0167 at an angle 88.09 degree. That gives us 5222.832 minus J 1403.9835 volt. This may be written in polar form as 5408.2477 volt at an angle minus 15.05 degree. Since the armature winding is star connected, line to line induced EMF E02 line equals to root 3 times E02, that is equal to root 3 into 5408.2477, that gives us 9367.4 volt or 9.3674 kilovolt. Now we shall calculate power supplied to the motor. P into equals to root 3 times VL into Ia cos phi 2. Using values we get root 3 into 11,000 into 60 into 0.8. That gives us 914.5228 into 10 to the power 3 watt or 914.5228 kilowatt. Let us summarize the results obtained. First case, when operating power factor cos phi 1 equals to 0.8 leading, we have computed power supplied to the motor P in 1 equals to 914.5228 kilowatt and line to line induced EMF E01 line equals to 13.042 kilovolt. Second case, when operating power factor cos phi 2 equals to 0.8 lagging, power supplied to the motor P in 2 equals to 914.5228 kilowatt and line to line induced EMF E02 line equals to 9.3674 kilovolt. Here we observe that amount of power supplied to the motor is same in each case, but under leading power factor condition, E01 line is greater than VL. This condition is termed as overexcited condition. Under lagging power factor condition, E02 line is less than VL. This condition is termed as underexcited condition. This indicates that field current required is smaller under lagging power factor condition. So today we have solved a couple of numerical problems on three-phase synchronous motors. By solving these problems, we have learned how to determine induced EMF and input power of a three-phase synchronous motor. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.